Welcome back. So, at the end of class last time, we introduced the concept of Gauss's law. In Gauss's law, we find that the electric flux through a surface, so that is this phi sign here that looks sort of like the Green Lantern symbol, is equal to the amount of charge inside of the surface divided by the permittivity of free space, a constant. This is useful because this is completely independent of the shape of the surface. That means we can choose a shape that fits our purposes to try and find the electric field at a given point. So let's try to apply Gauss's law to a point charge. So we want to find the flux through a sphere that is centered around the point charge. This is a good choice because the distance from the point charge to the surface of the sphere will be the same at every point on the sphere, so we can call that r. So the flux is equal to the electric field line at the surface of the sphere times the area of the sphere. And that is equal to the charge within the sphere divided by epsilon naught. We know that the surface area of a sphere is 4 pi r squared, so plugging that into the area and isolating the value of the electric field gets us the electric field is equal to Q divided by 4 pi radius squared epsilon naught. So we'll notice this is exactly equal to Coulomb's law. So from this you can see that Gauss's law helps us to find the electric field around a charge. In particular, one of the challenges of electrostatics is what happens when you start adding up a large number of charges and have them in unusual shapes and have to add them all together. Normally we solve this using calculus, but with Gauss's law we have a conceptual way of finding the electric field strength that doesn't necessarily require calculus. So the next situation that we want to consider is when we have a sheet that has an evenly distributed amount of charge. We'll consider an infinitely large sheet that has an even charge distribution over the sheet. So that means we need to figure out the shape of the surface that we want to use, this Gaussian surface, and the amount of charge that is inside of this surface. We want a surface that is symmetrical, so we're going to choose our surface as a cylinder that goes through the sheet, and it has an area that extends through both sides of the charged sheet. The electric field generated by the sheet is uniform, as we discussed last time, so the electric field at both ends of the cylinder is the same, and we will call that field E. The area is the area of the ends of the cylinder, because the electric field is exactly perpendicular to the surface of area A, and it's aligned with that area vector that is pointing straight out of the area. So there is two ends to our cylinder, so the total flux is 2 times A times E, because both the top and the bottom surfaces have a flux of EA, so you add them together to get a total flux of 2EA. So next we want to find the amount of charge within the surface. Well, the area of the sheet within the surface, so we will define that sigma, and so this sigma is the surface charge density. That means you have a certain amount of charge per area, say 1 coulomb per square meter. You've done volume densities before, I think, so like rho, for example, that is the density of the mass per unit volume. This is pretty similar, except now we are talking about a charge per surface area. So that means it's going to be per meter squared rather than meters cubed. The entire sheet is infinite in all directions, so that means the amount of charge inside of our cylinder is sigma times the area of our cylinder. So we want to put all of this into Gauss's law, and the areas cancel out, and we have the electric field generated by a flat charged surface to be the charge density sigma divided by 2 epsilon naught. So that means if you have the charge density on a plate, we can find the magnitude of the electric field generated by that plate. So now we want to apply this to multiple plates. So if we have 2 charged plates, both plates generate an electric field, and the strength of the electric field is given at a given point is the sum of the fields generated by the 2 plates. The trick here is you have to figure out which direction your field is pointing, because it could point either way. So here we have one positive plate to the left and a negative positive plate to the right, and they both have the same charge density called sigma, although one is negative and one is positive. So what is the field in the middle? Well, the positively charged plate generates a field that points to the right on its right side, and the field that points to the left on its left side. The red arrows here indicate the field generated by the positive plate. So between the plates, the positive plate generates a field that points to the right. The negative plate generates an electric field that points towards itself, right? Since your electric field tells you which way a positive test charge would go. So to the left of the negative plate, as shown by our blue arrows, the field points to the right. And to the right of the plate, the field generated by the negative plate points to the left. So if we look in the middle, we add the two vectors together and we get two arrows pointing to the right. So each charge density generates a field of sigma over 2 epsilon. So the total field in the middle here is 1/2 sigma over epsilon plus 1/2 sigma over epsilon. So it adds up to be 1 sigma over epsilon. If we switch the plates, the field would point to the left now, so it would now be a negative sigma over epsilon. So yeah, so this is the strategy for solving these. I think you guys have one to do soon where you look at the field outside of the two plates. Also notice that the field may have a different strength when you go from one area to the next. All right, so next we'll look at some more complicated situations with multiple plates. Good luck.